Hello everyone, welcome to the 12th episode of this series. In this video, we'll talk about computing determinants using row operations. So far, we have learned about determinants and some of their basic properties. In this episode, we're going to learn an algorithm to compute the determinant of a matrix. So the strategy we will use will be to use row operations to transform our given matrix into another matrix whose determinant we can compute very easily. What we know so far is that we can use row operations to put any matrix into row echelon form. So this begs the question, what is the determinant of a matrix in row echelon form? We're going to answer that in a more general setting. And for that, I'm going to introduce a few new special types of square matrices. So the first is called an upper triangular matrix, and uh, this is the matrix that has zeros below the diagonal. Then you have the lower triangular matrix, and um, this has the property that every entry that is above the diagonal is zero. And then we have the diagonal matrix that has the property that every term that is not on the diagonal is zero. Uh, so these are some of the examples. So in the first one, every term below the diagonal is zero. So this is our triangular. In the second matrix, every term above the diagonal is zero. So this is lower triangular. And in the third matrix, every term apart from the diagonal is zero. Uh, and therefore, this is the diagonal matrix. We usually do not put any restriction for numbers in the diagonal. They could be zero, they could be non-zero. So note that by definition, a square matrix in row echelon form is an upper triangular matrix which has ones and zeros on the diagonal. Uh, but it's also important to remember that not every upper triangular matrix is in row echelon form. So the reason upper triangle matrices are special to us is because we can compute their determinant very easily. So the determinant of an upper triangular matrix is just the product of the diagonal entries. In fact, the determinant of a lower triangular matrix or a diagonal matrix is also the product of diagonal entries. For example, if we have this 4 by 4 matrix, and since every term below the diagonal is zero, this is upper triangular, we can compute its determinant by just taking the entries on the diagonal and just multiplying them all together, and that will be the determinant. Similarly, in the second example, every term below the diagonal is zero, so this is also an upper triangular matrix, and therefore we can just take the product of all the entries on the diagonal, and we'll see that the determinant is zero in this case. Now, because any square matrix that is in row echelon form is also upper triangular, we can use Gaussian elimination to put the matrix into its equivalent row echelon form, let's say B. And while we do that, we keep track of how this determinant changes in a number. And let's say that by the end of our computation, the determinant of A and the determinant of B, where A is our original matrix and B is the equivalent row echelon form matrix, differ by a factor of R, then if our row echelon form has a row of zeros, then the determinant is going to be zero, and therefore the determinant of A is also going to be zero. And if we don't have a row of zeros, because A and therefore B is a square matrix, every row is going to have a leading one, and therefore the determinant of B is going to be one, because all the diagonal entries are going to be one. And if the determinant of B is one, then that makes determinant of A equal to R. Now, this method is consistent and practical, but there may be easier methods for hand computation. Now, we can tweak our previous approach slightly by changing the matrix into any upper triangular form instead of going to a very specific upper triangular form, that is the row echelon form. So this new tweaked approach is going to be very similar. We're going to use row operations to to change the matrix so that we can get something in an upper triangular form. And while we do that, we're going to keep track of how the determinant is changing under our row operations. And again, if determinant of A and determinant of B differ by a multiplicative factor of R, then if B has a row of zeros, then the determinant of B and therefore the determinant of A are both going to be 0. And otherwise, determinant of A is just going to be R. Okay, so let's look at an exercise. So we're given a 3 by 3 matrix and we want to use row operations to find the determinant. Okay, so to compute the determinant, we first switch rows 1 and 2 with each other, and because we are switching or swapping rows, we get a minus sign outside the determinant. Then we use row 1 to eliminate the entries in column 1 by adding multiples of row 1 to row 2 and row 3, and that does not change the determinant at all. And then we add row 3 times minus 1 to row 2, and again this is addition of a multiple of row to another row, so this does not change the determinant. And then we add a multiple of row 2 to row 3 to eliminate the entry below this 1. And again, the determinant is still the same. And in the last step, we factor out a 25 from the last row. And therefore, we have a matrix in row echelon form. And we know that since it's in the row echelon form, it's also in the upper triangular form. And therefore, the determinant of this matrix is just 1 times 1 times 1. And therefore, the determinant of the matrix A is minus 25 times 1. And that's just minus 25. Let's look at another exercise. So we are given another 3 by 3 matrix, and we want to compute its determinant using row operations. So the first step we take to compute this determinant is that we add row 1 times 2 to row 2, and we add row 1 to row 3. Then we get row 2 and row 3 to be the same, and then we can subtract row 2 from row 3, thereby getting a row of zeros in the last row. And now this is an upper triangular matrix. We can compute its determinant, and it's just going to be 1 times 1 times 0, and that's just 0. Okay, so let's look at another exercise. So in this problem, we're given a linear system, and we want to show that there is a unique solution to the system using determinants. So the first step we take is we rewrite this linear system into a more familiar form, and then we derive the coefficient matrix from it. So this matrix is a 3 by 3 matrix. The first column is all the coefficients of x1, the second column is all the coefficients of x2, and the third column is all the coefficients of x3. Then we put the coefficient matrix into upper triangular form using a series of row equations that I haven't mentioned here, but you're very welcome to check that you eventually get the determinant to be minus 4. So because the determinant is minus 4 and therefore non-zero, the definition of determinant tells us that C is invertible and therefore C inverse exists. Now, since the coefficient matrix is invertible, the system is uniquely solvable, and the solution is given by the product of the matrix C inverse and the vector of constants 12, 0, 6. Now, note that the determinant of the coefficient matrix being non-zero told us that the linear system has a unique solution. We didn't even need to check the constant terms in the system. So in other words, if we're dealing with a square matrix and if its determinant is non-zero, and if the square matrix represents the coefficient matrix of a linear system, then for every possible vector of constants, there is going to be a solution. And with this, I would like to end this episode. Hope things were clear. I will see you guys soon. Up until then, happy learning.